So the title of my talk today is Two-Phase Fluid Leakage Through Faults Using a Multiscale Analytical Numerical Modeling Approach. I want to acknowledge my collaborators, Jan Nordbotten at University of Bergen, Florian Doster at Heriot-Watt, and Mike Celia at Princeton. So the application that I'm thinking about here is CO2 storage into deep saline aquifers. But obviously, the methods presented here are not limited to this application, but I'll be talking about it, the model with respect to this application. So what I have here is if you take a slice through the earth in a sedimentary basin, what you will have are layers of different properties. And so, for instance, what's going on here is CO2 injection here into this target aquifer where there's brine, and because of the density difference between CO2 and brine, you would have the CO2 at top. And then it would stay there because of the cap rock, which is a lower permeability unit. But a big problem, or there is a concern for leakage if you have leakage pathways such as abandoned wells and faults, and this is a problem because you want the CO2 to stay in this target aquifer. So an important quantity that we want to characterize is what is the leakage rate coming through this fault, and also abandoned wells, but what I'll be focusing on is what's happening right here. In general, the objective is to develop a computationally efficient model that captures the essential processes governing leakage through faults as an alternative to grid refinement and three-dimensional numerical models. So basically, I've developed a multi-scale model using analytical and numerical methods. So the outline for the rest of my talk is first the fine-scale model for fault leakage. And the three components are horizontal flow in the aquifer perpendicular to the fault, pressure correction within the, near the fault, and to think about the effect of fault properties. And then I'll be presenting the multi-scale modeling framework. First, I'll talk about the core-scale numerical model. In this case, I'm thinking about 2D vertically integrated model, and how to integrate some of the fine scale information into the core scale. I just want to make a quick note about what scales I'm thinking about. So for the core scale, I'm thinking about, I'm thinking about large basin scale models. So we have domains in the order of up to hundreds of thousands of square kilometers. So you have grid blocks in the order of kilometers. So in the fine scale model, we're thinking about meter scales, tens of meter scales. So this is the fine scale model. What you see here is, remember, if we think about the previous couple slides back, so I'm just looking at one side of a fault. And here's the fault zone in the gray. So you have a cap rock, a low permeable unit here. And here's your saline aquifer. And here you have, let's assume density segregation has occurred, and you have CO2 on top and brine on the bottom. And then you would have leakage like this. So first, I'm going to briefly talk about characterizing, defining the flow field to the fault. Two speakers before, the first speaker talked about the different fault systems, talked about conduits systems, barrier systems. What I'm considering here are conduit barrier fault systems. However, I can extend this to look at conduit systems as well. So a conduit barrier system. So what we're assuming here is no flow, and we're assuming basically an impermeable fault core. And the gray zone is the damage zone, which would have higher permeabilities in the aquifer and cause leakage. So you have properties of this damage zone, I call it just the fault here, and in the different directions. So we're just looking at the 2D, and then properties in the aquifer. And obviously what we're trying to, one of the key important parameters again is the leakage rate that you get. Another important thing is the width of the fault and boundary conditions here, thickness of the CO2. So the basic components of this model is an analytical solution for horizontal flow perpendicular to the fault, and a fault model representing effects of the fault properties. And you can find more information in this paper. So back to the fine scale model. So again, an important quantity that we want to quantify is the leakage rate. So this is the two-phase flow extension of Darcy's law. And so we have brine and CO2. And so we want to know the leakage rate through here. So what's driving this is the pressure of the fault, pressure right here. If you think about a core scale model, what you would get is a pressure for the whole grid block. And because there's leakage occurring, the pressure at the fault is different than the pressure at the whole grid block. And so you need to correct for that. You need to accurately determine that to accurately determine the leakage rate. So this is the approach to determine the corrected pressure. So again, we need the pressure in the fault to determine the pressure gradient driving flow in the fault. I showed you a schematic for pressure at the fault in terms and how it relates to vertical flow through the fault, but this correction is also important when you're thinking about horizontal parallel flow within the fault as well. So just to talk briefly about the reconstruction. So basically, this is the corrected pressure, and that is, this big P is the core scale numerical pressure, and then you can derive the delta P using the analytical solution. And then using those two, you can get a corrected pressure term, which you can use to find the pressure at the fault. Okay, so I'm going to briefly talk about the effect of fault properties. So what I'm showing here in this graph is leakage rate here, and these are steady state solutions. And this is Q prime D is the proportion of the leakage that is brine. So what that means is when you have Q prime D equals 0, all you have is CO2 leaking out. And then at a certain leakage rate, you start having brine also leaking out. You can determine this point, depending on the boundary conditions, analytically, this leakage rate. And then and you can also determine the maximum Q prime D value analytically. And what you find is that the fault property is important in characterizing this curve in the middle. Okay, now I'm going to talk about the multiscale modeling framework and how we use the fine scale model that I just talked about in this modeling framework. So again, the core scale model that I'm thinking about is a 2D vertically integrated numerical model, and this is a 2D space. And let's suppose that we have a grid block here with a fault on one side. And if we blow that up, the things that we want to know are, we want to understand, we have to characterize the flow to the fault and flow through the fault, not just in the vertical direction, but also in the horizontal direction. And this is what really differentiates this approach, the models for fault leakage from models for leakage through wells, which is a radial, which the effects are more radial. The geometry is clearly different. So briefly, I just want to talk about the core scale numerical model. So again, 2D vertically integrated numerical model. Here we assume vertical equilibrium, negligible capillary pressures, and then compressible fluids for the equations that I showed here. So these are the mass balance equations. And here's Darcy's law. And all these variables are vertically integrated. And so you can see this is a vertically integrated flow for the brine. And a couple parameters that I want to highlight are P, this pressure. When we talked about the core scale pressure value and how we correct that. And so pressure, and also I didn't talk about this is actually the thickness of the brine and how we correct that, but you can correct that in a similar kind of approach. And that's what we do. So just the multi-scale model features. The core scale model is the 2D vertically integrated numerical model. Fine scale model components are the horizontal flow to the fault, perpendicular to the fault, vertical flow through the fault, and horizontal flow through the fault. I didn't talk too much about this, but just to give you a schematic, and I'm not going to show the derivations, but basically these are the core scale numerical grid blocks. And let's suppose that there are two grid blocks adjacent to each other with a fault running through. And normally you just have a single pressure value for the whole grid block and also H value. But obviously, if you want to think the flow through here is definitely very different from the flow in the bulk aquifer. So again, if you recall the slides where I talk about the pressure corrections, you would use that information to determine the pressure here and drive and then determine the flows in these directions and also in here. And so you would use that information and feed it into the core scale model. And that's the multi-scale modeling framework. Okay, so just quickly show you some results. I'm just going to focus on, this is just the horizontal flow perpendicular to the fault. And so the first three are different analytical solutions. The green one is the vertical equilibrium solution, and the full ODE is a solution that relaxes the vertical equilibrium solution, which is important in some cases, especially near leakage features. And basically it just shows you two different options. Here's where there's only CO2 leaking, and here both of these solutions match the numerical simulation, which is in black very well. Here it's matching the full ODE solution, and there's more details on that, but there's ways to determine which solution you should select based on some simple calculations. Okay, so this is just a quick example. We just have three grid blocks with the fault that is extending throughout those three grid blocks. And here's the pressure. You have a drop in pressure at the fault. And this is the thickness of brine. So as you have leakage, you have the brine interface moving upwards in the fault. And this is a quantity that you want to calculate, which is the total leakage. So, so the leakage of both CO2 and brine, where it's applicable. And so I have I have three lines here, but the two ends are the same value. So it's the red line actually has a blue line underneath it as well, and because it's symmetrical. But so you can see the difference between the ends, and this is actually the proportion of the leakage that's brine. And so this is these are some example simulations. That brings me to the summary. I presented a multi-scale model for leakage through faults using a fine-scale analytical model and a core-scale numerical model. This multi-scale model can be useful for efficient simulation of large basin-scale problems, especially if you want to run it in kind of a Monte Carlo framework, and the efficiency becomes important. And this modeling framework can be integrated into a multi-layer model, but also with multiple fine-scale leakage features. In a basin-scale model, in the basin, you will have faults, but also abandoned wells. And you can combine all those leakage features into a single model using this kind of a framework.
So does anyone have a question for Mary on the talk?
I wonder if the vertical equilibrium model is assumption is valid for multi-layer medium.
So in the fine scale, what we found that is what I showed in the one paper is that the vertical equilibrium assumption can be you need to relax it, and that's one of the results I show here, right? So when you have two-phase leakage, it depends on your domain, how long your aquifer is, the thickness, and you can determine whether it's applicable. But for a really for the core scale numerical model, it should be okay, especially if you have thin information.
Thank you.
Right. Thank you.